All right, guys, let's get to let's finish 4.1. So we're going to do the direct proof in just a moment. So generalizing from generic particular. So in order to do this kind of like this type of proof, we got to show that every element of a set satisfies a certain property. So suppose X is a particular. Suppose X is a particular but arbitrary chosen element of the set. And then we will show that it satisfies a property. So basically say let's let X be something, and then we let it be any X, and we show that it works for all those X's. So if we leave it general or arbitrary, then we can start doing the proof. But here are the steps from the book. So number one, the first thing you should do is express a statement. It should be proved in this mathematical form. That way you can kind of see or think about how we're going to do this. And then start by the proof by supposing X is a particular, but arbitrary, like we said, chosen element of D, for which the hypothesis is true. Okay, and then we will show that the conclusion of Q is true by using definitions previously established, results, and etc. So basically, we use the logic, we use definitions and properties that already exist to prove a new definition, a new theorem or property. Okay, that's what we're gonna do. So here's a random one from the book. Example 4.1.7. So this is a direct proof type. To prove that the sum of any two even integers is even. Okay, so here we go. So we should first start by rewriting it in mathematical terms. Let's change it into a formal argument. So we want to show that for all integers m and n, if m and n are even, then m plus n is even. So this is what we're trying to prove once we put it in formal terms. So we should use the definition of being even and odd, which we wrote down last time in part one. So since m is even, sorry, we should say it this way, since m is even, since m and n are even, then they can be written as this. So m would be equal to some integer by definition times 2, and n would be the same, some integer times 2. So let's say 2s and r, where r and s are excuse me, are integers. Yeah, that's right. Okay. So we can show, right? So we will add them. We want to show this. Since they're even, therefore, m plus n is equal to 2r plus 2s, which is equal to 2 times r plus s, which is even by definition. So this proves our statement. So we use a definition to rewrite each element. So this is how we start, right? rewrite the question, math statements, and then we say, okay, well, what do I need to prove this? Well, I need the definition of even. So right here, I go ahead and change m and n into what it means to be even, some integer times 2, some integer times 2. Then we show that adding them together with the definition can be shown to still be written as a definition. R plus S is some integer times 2, which makes it even. So that's direct proof using definitions. Now let's see what's next. Okay, let's do one more, and then we'll go to another section. Let's prove the following theorem. For all integers R and S, if R is even and S is odd, then 3R plus 2S is even. So this one's pretty much already in formal form. So we just need to remember what are the definitions of odd and even, right? So they said R is even, S is odd. Okay, so since, let's use the definition, since R is even and S is odd, then that is to say that R is equal to, so R is even, 2 times, I will just make up some letter, 2 times W, and S is equal to 2, let's say U, I guess. So it doesn't matter. 2U plus 1, where W and U are integers. All right, so now we have some facts that we can use. Therefore, let's start doing the math here. 3R plus 2S is equal to 3 times 2W plus 2 times 2U plus 1, right? Doing the substitution, just basic algebra substitution, right? There's my RW, 2U. So this is just some integer times 2, some even number. This is some odd number, integer times 2 plus 1. So that will be 6W plus 4U plus 2. Now I can factor 2 out of the entire thing to give us 3W plus 2U, right? Plus 1. Thus, by definition of even, 2 times 3W plus 2U plus 1 is even. You see how we're just using the definitions, and we're trying to make a, so remember what they're asking for. They want to know that this is even. So that means I need to be able to rewrite this as something times 2, because that is a definition of even. So first I use a definition of even here and odd there, do some basic math, factor by 2, and then you show that this now fits the definition of even. So that proves that yes, this will be even.